In the previous video, we saw the definition of a vector bundle abstractly. And now I want to talk about some important things that we can do with that definition of a vector bundle. I mean, one of the first things that we should be thinking about is, we've defined a vector bundle abstractly so that, we sort of imagine, we have our manifold, and above each point in our manifold, we imagine we have, hovering this vector space. And so because we have access now to linear algebra, right? We have some sort of collection of vector spaces parameterized by this geometric object. We should start asking ourselves, well, what features of linear algebra carry over here, right? I mean, we're dealing with vector spaces. So what about vector spaces carry over? Bases, direct sums, tensor products, right? So this is the first thing we should start asking ourselves about, is like, okay, well, what can we actually recover in this sort of more general setting of linear algebra? And indeed, all of these things I just mentioned carry over. And they're going to be very important for talking about the proper definition of tensors in physics, right? So if I have two vector bundles, say E and F, right, both over the same base space, I can form, now again, I'm not going to go through all the proofs in detail because the series is quite long enough already. But I can form the direct sum of these bundles, right? So, well, how do we think, how do you think we're going to define the direct sum, right? Well, let pi sub E be the projection map that comes with E. Remember, that's part of the data of a vector bundle in this projection map for F. So first, a bit of notation I didn't actually use last time. As a shorthand for the fiber above some particular point little x, we will use, E subscript x. So the total space subscript the point in the base space. So we use that to denote the fiber. Well, how should I define the direct sum? Well, it should be, right, it should respect the fibers, right? So I want to define the direct sum in such a way that for this new vector bundle, the fiber above each point, of course, is just going to be the fiber of E above that point, direct sum the fiber above F at that point, right? Now, of course, you have to go through, you have to check the definitions, see that this does, in fact, define a vector bundle. But it does, right? So direct sums, we can form, same thing. Of course, this is extremely, obviously, it's a series about tensors, so of course this is going to be an important one. We can form the tensor product. And again, this is just going to be fiber-wise tensor product of vector spaces. Some other important ones for this series, though, are going to be the Hom space, right? And again, these are all just things that exist in linear algebra, right? So the Hom space, what is that going to be? Just like we can take two vector spaces and form the vector space of linear transformations between them. Again, we can take two vector bundles and form the vector bundle of linear transformations between them, which again is just fiber-wise, right? What's the fiber of this vector bundle going to be above each point? It's going to be the Hom space of the fibers. One case that's particularly important of this, of course, is the dual space, right? So if we have the Hom into the real numbers, right? So, okay, I'm abusing notation here, right? What do I mean by the real numbers? Is probably a number of different non-equivalent ways we could make a fiber bundle with the real numbers assigned to each base point, right? I mean, we saw in the previous video the case of S1, where we had, the tangent bundle of S1 just was this infinite cylinder. And then we also had this Mobius sort of bundle of S1, where again, this was this was just a copy of the real numbers at every point, but all sort of twisted up in this weird way, right? Well, I didn't prove to you that those are non-equivalent, but it turns out that the Mobius bundle is, normally one of the first non-trivial vector bundles that you encounter or prove is non-trivial. So this notation, to reiterate, is a little bit abusive here, but there is a very natural way to take a vector bundle and then to talk about the dual of each of those fibers, and then therefore talk about the dual bundle. And this is really important. In fact, when we talk about integration on manifolds and therefore integration in physics, and we talk about vectors and covectors, we're really going to need this definition. What's another thing that's really important in linear algebra that we normally learn about and work with, in your first real linear algebra course? It's a basis of a vector space. So another question is, well, does the notion of a basis carry over to a vector bundle? And yes, but not every vector bundle has a basis. Well, first off, what should that even mean, right? Because a vector bundle is not a vector space. But let's suppose that we have a vector bundle, right? We got E, we've got our projection map, and each fiber is a vector space. So we might think then, well, okay, what a basis for a vector bundle should be is an assignment, to each fiber. Let's say all of our fibers are dimension n. It should be an assignment of n vectors providing us with a basis of that fiber. But again, remember that we don't want to forget about the fact that we are doing geometry here, right? Just like in the case of when we're talking about vector fields, we want things to sort of vary continuously, we want things to vary smoothly. So there should be some sense in which we have a smooth assignment. Well, again, we're going to talk about this using sections, right? So a section, if we have a section of our vector bundle, right, that just means above each point, it's picking out some collection of vectors. So the right way to frame this then is to imagine that we have a collection of sections, right? So maybe we have n sections, and what we want is that each of these n sections, when evaluated at each point in the manifold, we want those evaluations to give us a basis of that fiber, right? So this should be a basis of EX, right? So the section built into the definition of the section is that it is smooth, right? But now the interesting thing is that this doesn't always exist. Classic example is the so-called hairy ball theorem, right? So the sort of layman explanation is that, if you imagine a sphere with a bunch of hairs, you can never comb it so that there isn't a cowlick. Well, if we imagine what that should mean, so let's think about the tangent bundle, right? Each of those fibers is two-dimensional. We have a two-dimensional tangent space to the sphere at every point. And what ends up happening, though, so if we imagine, we're trying to pick some pair of orthogonal vectors at each point, but remember, essentially what the hairy ball theorem says in so many words is that a vector field, right, in order for it to be smooth and avoid that cowlick, it has to vanish, right? Every vector field vanishes at some point. So a section, right, if these are both coming from two different sections, an individual section in our tangent bundle is a vector field. And the hairy ball theorem says that has to vanish somewhere. So even if, some like over half the sphere, you could pick these sections that carve out a basis everywhere, one of those has to be the zero vector at some point, and therefore the two of them together can't be a basis at every single fiber. And then you could say, well, let's toss in a third one, right? But then you no longer have a basis because all three of them at some fiber where they're all three non-zero, it's a spanning set, sure, but they're not linearly independent anymore. However, so this is something called a frame, right? So if we can find such a global thing, we call it a frame instead of a basis, right? So a frame is a collection of sections where at each point that collection gives you a basis of that fiber. However, we can find a local frame. Recall that at each point we can find some open set so that this so that the inverse image of that open set is simply diffeomorphic to just a Cartesian product, right? And so locally, we can find a frame. It's not going to work for the entire vector bundle, but it will work over this open set, right? All we need to do is just pick any old basis of r to the k, so v1 to vk. And now we define sections. So how are we going to define these sections, S1 up to sk? Well, we simply define it so that S1, well, let's say Si at y is going to be equal to vi for all y in u. And now it's, it's just a matter of proving that this is in fact a smooth map and that it is a section of the projection map. Now, technically, I haven't even defined morphism, let alone isomorphism for vector bundles yet. So technically, I haven't finished defining vector bundles for you. And so perhaps that'll come in the next video, but I just want to point something out. We already saw that the tangent bundle for S1 is essentially the trivial bundle, right? So what does that mean? It means isomorphic, and we need to define isomorphic, but already in pictures, we were able to realize this as being the same as the trivial bundle, right? So that means by this argument, right, because it's globally trivial, by the same argument, that means I can find a global frame for the tangent bundle for S1. One question, a famous question in differential geometry, is for what spheres can we find a global frame for their tangent bundle? It turns out that the only spheres we can do this for are S0, the zero-dimensional sphere, right? This is just two disconnected points. S1, as we've already seen, S3, and S7. What's really interesting is that it is not a coincidence that the dimensions of these spheres are exactly one less than the dimensions of each of the normed division algebras, being the real numbers, the complex numbers, the quaternions, and the octonions.